Modern large language models require server clusters of staggering physical scale. Training a frontier model consumes tens of thousands of GPUs, running continuously for months. To estimate compute, we use C equals 6ND, 6 times model parameters times dataset tokens. But this theoretical linear path hits a dense web of memory bottlenecks on hardware. State-of-the-art clusters rarely achieve over 45 to 60% model flops utilization, or MFU. The demand for calculations scales in a perfect straight line, yet the hardware's ability to execute those calculations drops by nearly half the moment the system runs. Resolving this discrepancy requires applying a strict first-order approximation. We have to isolate the dominant variables in the transformer architecture and map them directly onto the physical pathways of the hardware. Scaling laws provide a theoretical ceiling, but actual performance depends on how efficiently matrix mathematics translate into the physical movement of electrons. Inside a transformer block, the two defining dimensions are the parameter count, n, and the token volume, d. This is the forward pass. A 1 by d input vector multiplies against massive d by k weight matrices. Processing a single token through a single parameter requires two floating point operations, one multiply and one add. That equates to a baseline cost of 2ND. During the backward pass, the computational burden doubles. To propagate errors and update the model, the system must execute two parallel operations, calculating the gradient with respect to the input and the gradient with respect to the weights. Each requires its own 2ND operations. Adding the 4ND from the backward pass to the 2ND from the forward pass yields the final 6ND total. Yet this formula entirely ignores essential operations like layer norm, softmax, and the core attention mechanism. This is the logic of the first-order approximation. Because model dimensions are so massive, the multi-layer perceptron layers dominate the calculation, making the sequence length penalty negligible. But push the context length to an extreme, say 1 million tokens, and the attention penalty overtakes the matrix math, making the 6ND approximation ineffective. The 6ND model is accurate because it is deliberately incomplete. By stripping away nonlinear noise, it isolates the core computational engine driving the hardware. Knowing the exact flops requirement exposes the hardware problem. Model flops utilization measures the percentage of useful compute executed against the hardware's theoretical peak. This chart is the roofline model. It plots theoretical performance against arithmetic intensity, the amount of compute performed for every byte of data fetched from memory. Massive, dense matrix multiplications are highly efficient. Data is loaded into the cache once, and the tensor cores execute thousands of operations, locking performance at the theoretical ceiling. Conversely, operations like layer norm or activation functions execute very few calculations per byte. They drop onto the bandwidth-limited slope. During these low-intensity operations, the tensor cores sit idle. They are waiting for data to travel from the video RAM to the compute units. The irony of AI compute is that minor non-matrix operations, the exact variables ignored by the 6ND equation, cause the most severe hardware starvation. To mitigate this, engineers employ operator fusion. Combining normalization and activation into a single step reduces memory fetches, pushing the workload up the intensity curve. MFU isn't a measure of how hard the hardware works. It is a measure of how effectively the workload avoids memory bottlenecks. Those bottlenecks are physical locations within the server node architecture. Data gets stranded precisely where the hardware layers intersect. This schematic highlights the PCIe slot. It is the generic serial highway connecting the host CPU and system memory to peripheral devices like the GPU. Data follows a sequential path, moving from storage into the system RAM, processed by the CPU, across the PCIe bus, and into the GPU. Even advanced PCIe connections max out around 64 gigabytes per second. For tensor cores designed for terabyte-scale throughput, this creates a significant bandwidth deficit. The CPU acts as a sluggish middleman. The GPU waits for the CPU to pass data across the PCIe bridge, instantly dropping the MFU. This node topology diagram outlines the modern architectural workaround, GPU Direct RDMA. It routes data straight from network storage directly into the GPU's memory, bypassing the CPU and the system RAM entirely. Once data finally reaches the GPU,
The high-speed training loop abandons standard connections, relying instead on microscopic, bespoke interconnects to maintain computational momentum. Inside the chip, arithmetic intensity bottlenecks are solved by high bandwidth memory, or HBM. This cross-section shows how HBM achieves terabytes per second of bandwidth. It abandons traditional copper traces, mounting the GPU die and memory stacks directly onto a nanoscale silicon interposer. This extreme internal bandwidth serves one purpose: to continually feed data into the second forward pass matrix multiplications without ever stalling the compute cores. But the for-end backward pass creates an external challenge. The massive gradients generated during backpropagation must be synchronized across hundreds of separate GPUs simultaneously. That synchronization occurs during the all-reduce phase, which requires a dedicated mesh network known as NVLink. NVLink operates on a point-to-point architecture. It delivers nearly 900 gigabytes per second, circumventing the serial limitations and protocol overhead of the PCIe bus. By pooling memory access at these speeds, NVLink unifies separate physical GPUs into one logical accelerator. These interconnects are the physical manifestation of the 6ND equation. They are engineered to prevent data starvation. Zooming out from the silicon interposers to the data center floor reveals the complete stack. The mathematical simplicity of the 6ND calculation only works because the physical hardware topology is engineered to force it to be true. This matrix shows how theoretical mathematics map directly to physical solutions. The second calculation of the forward pass is physically solved by the extreme bandwidth of the HBM interposer. The fourth ND requirement of the backward pass is physically solved by the NVLink mesh architecture. Optimizing an AI cluster is a physics problem. It requires minimizing the exact physical distance electrons must travel between processing steps. True mastery of LLM scaling means abandoning theoretical abstractions and designing exclusively for the reality of physical interconnects.